Um, yeah, I just went ahead and started the archive. And also let me pull up the e-board. Okay. And also got the lab textbook. So what would you like to get started with?
Personally, I'm kind of stuck on number 2, doing the wavelength.
Okay, is that number 2 of, that's the light and spectra, correct?
Correct. Number 2 and number 3 is where I'm having trouble too. I can't get my measurements to match anything in the table in number 3.
Oh, okay. Let's see, number 2, the color and the wavelength. That is for the unknown element?
Correct.
Yeah, okay. Let's see, I'm trying to think if I can pull up the image into the whiteboard.
Well, I got as far as the everything but doing the wavelength, and I think it's something I'm just missing, that it's very simple.
Well, actually, I could maybe draw something really quick. There is, I mean, what you do is you measure the position of the lines in centimeters from the left edge, and then there's a scale bar that tells you how many angstrom there are per centimeter, and then you multiply by that conversion factor. And I think the left edge of the spectrum starts at 4,000 angstrom, so whatever wavelength you calculate from the position, you have to add 4,000 angstroms to that. See, let me see if I can draw a little spectrum here.
So if I get a line at 2.6 centimeters, I should come out with a wavelength of 4336.4.
You don't have the numbers in front of me right now. Would that be, what color line would that be?
Looks like a really dark blue line, the indigo-ish color.
Okay, yeah, I mean that's definitely in the 4,000s. Is that the blue line that is closest to the edge?
Yes,
closest to the left,
the really dark blue line that you can see on the left-hand side.
Yeah, 4,300. Yeah, what do you get for the next line?
I measured the bluish one, like the second little bluish one to the right over, at 3.8 centimeters. So I came out with 4491.7.
Well, what did you get for the red one all the way over on the right?
The red, I got 15.1 centimeters for 5953.9.
5.9. Is that the furthest one that you got? What was your scale factor? What?
For my scale factor, I have 129.4 angstrom per centimeter.
Okay. Yeah, unfortunately, you don't have the numbers, but do you have a stab at an element? What element you think it might be?
Since my numbers are all over the place and don't really match anything in the table, I mean, some of them are kind of close, but then others aren't close at all, so I was scared to guess.
Well,
if I had to make a guess, I would say it's probably helium, because I can see clearly 5 or 6 different distinct lines, and helium and argon and mercury are the closest that have that many listed, and then helium is the closest to my starting number.
So you have most of the lines that you have match up with helium lines, correct? So if you look at the values, mean, if you look at your first line, you said it was 4,300 something, right?
4336.4, and it was at 2.6 centimeters.
Yeah, and then, I mean, the first helium line listed here would be at 4,471. Yeah, what about the second line?
My line is at 4491.7. So that's kind of close to the 4580.
Yeah. Oh, sorry, my dog. Yeah, I'm just kind of, surprised that you didn't get something like in the 6,700 range.
Let me look up the
Okay, well,
I mean, basically,
okay,
helium
I
is
guess
the correct answer. Make some colors in here. Yeah, now the unknown spectrum, is from a different source than the helium lines that the table 1 lists in terms of the wavelength. So that means, the lines that you see, you may not see exactly the same number of lines, or they may not, not all of them may be as prominent, but you should get the best matches if you go with the 4 or 5 most prominent lines that you see in the unknown spectrum. You should get the best overall matches with the helium lines that are listed in table 1. Just making this up here. Okay, so let me make a scale bar in here, and okay, and let's say um, okay, so let's say that this scale bar equals 1,000 angstroms. And also the left edge here was at 4,000 angstroms. And the right edge is at 7,000 angstroms.
Oh my gosh, there's 3 of us in the other room. Let me get them in this one.
Oh, great. Okay. Glad you caught that. Okay. So then what you would do to figure out the wavelength, you would take a ruler. See, I'm just going to change the color here. So your first step would be measure the length of the scale bar in centimeters. Now, of course, the length that you measure, since you're measuring it on a computer screen, depends really on the resolution and the size of your screen. So everybody might get different length measurements for the scale bar. Because I don't think I have a ruler with me now. Okay, well, let's assume the scale bar would be you know what? Let me see if I can find a ruler real quick. I'll be right back. Okay, got one. So even though you might get different centimeter readings depending on the resolution and size of your screen, but because you have the scale bar in centimeters and you have the measurement of the distance of the line from the left edge in centimeters, so that sort of divides out. Okay, so for my scale bar here, I'm getting something like 3.6 centimeters. Okay, so it's 3.6 centimeters. Okay, and then we know that the scale bar is 1,000 angstroms, and that's what I sort of guesstimated. So the next step would be to calculate the conversion factor. So we want to figure out how many angstroms we have per centimeter. So 2 would be or we could call it the scale factor. How many angstroms per centimeter? So that scale factor then would simply be the 1,000 divided by the 3.6 centimeters. So 1,000 angstrom divided by 3.6 centimeters. And let me pull up a calculator really quick. Okay. Divided by 3.6. Okay, so we have something like 277.8 angstroms per centimeter. I think in the lab, it should come out, I mean, if you, oh, wait a minute, that's for the second scale factor. Okay, so the third step would be now to measure the distance of each of the lines from the left edge in centimeters and then multiply that by the scale factor to get it in angstroms and then add the 4,000 to it. So step 3, fortunately that doesn't all fit. So length, let's actually say distance, so measure that in centimeters. Well, okay, let me go ahead and do a couple of measurements here and write those out so then I can start a second page, once we have the measurement. I'm not going to measure all the lines because obviously that would, take too much time. Let's just measure maybe let's see, how about we'll measure the dark blue line? How about that? I mean, once you multiply the scale factor, you should all get very similar results in terms of how many angstroms that is. So only your centimeter readings might be slightly different. And then later on for the second time, when you look at the shifted spectrum versus, the redshifted spectrum versus the regular spectrum in the second part of the lab, since you're measuring from the lab textbook, there you actually you should all get the same centimeter measurements and the same angstroms. Okay, but in this case, for the dark blue line, the centimeter distance from the left edge is just 1.5. Maybe I can still manage to write that in here. Oh, getting a little bit cut off. Okay, so let me go ahead and, yes.
I drew a line by mistake. I'm sorry. I was trying to move my screen up.
Oh, that little tiny
we can only see from number 3.
Yeah, okay, let me just give this a title real quick. Okay, so that would be Light and Spectra, the unknown. Oh no, what happened? Uh-oh. Oh no.
I didn't do it this time.
Here, hang on. It might have been me. Okay. Shoot. Such a nice slide. I should just save these things earlier. Maybe I was trying to, maybe I hit a wrong key or something. Okay. Yeah, I remember that happened last time, several times. Let's see, well, how do we do this? Let me just see how quickly I can. Oops. I'm just going to try to make it real quick. Okay. Okay, and then I'm just going to put in maybe a blue line here. green line, and a red line. Okay, and then we have the scale. Actually, I'm going to put that over here. Okay. So that's my scale factor. And yeah, so I'm just going to call that, let's call it, I don't know if it was, we could just call it 700 angstrom because it's a little bit shorter. Okay. Okay, now I'm going to write the centimeter measurement here for the scale factor. And that's going to be, I'm just holding the 0 to the left edge. Okay, that works out to be 2.5 centimeters. Okay, 2.5 centimeters. Okay, and I'm just going to label the edges here again with the wavelength. So the left edge, actually let me put that in black. Left edge was 4,000 angstrom. The right edge was 7,000 angstrom. Okay, and so the scale factor in, let me put that down here. We just say A since I used some sort of other numbers for the previous slide if you have already written something down. So the scale factor would be the 700 angstrom divided by 2.5 centimeters. So 700 divided by 2.5. So there would be 280. 280 angstrom per centimeter. So for every centimeter that we measure here from the left edge to where the line is, we have to multiply that distance in centimeter measurement by 280.
Professor?
Yes.
Okay, what threw me off is on the scale in the problem, it says 6.2 centimeters equals 802 angstrom. So does that 6.2 not play into the formulas at all?
Oh, is the 6.2 on the screen? Or where do you see the 6.2?
On the figure? The figure says that the line measures, it says 6.2 centimeters. Oh, I'm sorry. Never mind. I need to go to sleep. My bad. No, I measured it. I measured it and it was 6.2. So never mind.
Okay,
never mind.
That's fine. Okay, so for you definitely want to work with the 6.2. Okay, so what I'm measuring here on my screen, I get, this time it's 12 millimeters or 1.2 centimeters of so the blue line distance of blue line from left edge equals 1.2 centimeter. Okay, so then step C would be to convert the centimeters of the distance of the blue line from the left edge to angstroms. So we need to multiply that by the conversion factor, and then we'll change the centimeters into angstroms. So the distance in angstroms would be 1.2 centimeters and then times 280 angstrom per centimeter. So 1.2 times the 280. Okay, and that turns out to be 336 angstroms. Okay, so now we know that the distance in angstroms of the blue line from the left edge is 336 angstroms. But the total wavelength, we have to add the 4,000 to it because the left edge doesn't start at 0. It already starts at 4,000 angstrom. So then the last step would be the total wavelength where we need to add 4,000 angstroms for the left edge. Okay, and that would get us 4,000 plus 336. So that would be 4,336 angstrom. Okay, so that would be the absolute wavelength of the blue line. So then you would just go through and select the next line, and every line you want to measure from the left edge. So you don't want to measure the distance between the lines or anything. See, let me write that in there too. So measure each line from the left edge. Because then you can go through the same procedure every time. Whatever the centimeter distance is from the left edge times your conversion factor and then plus 4,000. So that should give you all the values.
I have one question. Where does I see that you actually put the values of 4,000 and 7,000 in. But where did you get 700 and 2.5? Is that, would that be given?
The scale, the length of the scale factor, if you bring up that image, then there should be an angstrom value with the scale bar that you see there. let me just go in and check real quick. Yeah,
I
I'll
was
be right back.
having a problem pulling that up in WIMBA. I just want to make sure that was given, because if I need to figure, because I'm not figuring out how you are to get those two numbers. So, but if they're given, that's cool. Then I get it.
Yeah, I'm just going to try to look at it really quickly.
It's 802 in the problem in the lab.
Okay, so
I haven't done any of it yet.
Mm-hmm. Okay, yeah. So the angstroms would be given, and then because you're sitting in front of your own screen, you would do the centimeter measurements. But all the angstroms are given, so it's 802. Okay, yeah, that sounds about right. Okay, well, I mean, we can go ahead and go through the calculation and assume, okay, let's say we identified our spectrum as helium, and compare, the first blue line here to the first, to the closest line that is given in the helium spectrum. Okay, so let me clear that slide. Now that I've saved it, let me just save it again just to make sure. Okay, and so now we're going to just do the first row of the data table. Okay, so in column A, we have our experimental value. Oops. And that was our 4,336. And again, you may get something different because you're, working with the real thing. I just pulled my number out of the hat by making up a spectrum. Okay, and then in column B, we're putting down the known value. So this is where you want to match up the number that you have with the line that is closest, the element that you think it is. So if we think it's helium, then we would say something like, well, the 4336, that's closest to the 4471 line. So we're going to match it to the known value of 4,471 angstroms for helium. Of course, you use helium for the entire table, once you've settled on helium. So let me actually write that up top with the helium. Okay, so let me put that up here. Okay, blue. Okay, so then step C, you want to take the absolute value of the difference. Because depending on what you've measured, you may get something smaller, as I did, or something larger than the wavelength that you compare it to. But we're only interested in the absolute value of the difference. Oh, I meant to do that in black, but anyway. Okay. So then we have, 4471 angstrom minus 4336 angstrom now it turns black. Okay, let me pull up the calculator again. So 4471 minus 4336 My seventh grader could probably do that in her head. 135. Okay. So that's 135 angstrom. And that looks like it's a lot, but if you compare it to the, total wavelength that we're dealing with, which is in the 4,000s, then it actually won't come out as that much. So in column D, we're going to take the ratio of the difference over the known value. Okay, so that would be D. Difference over the known value. Okay, so the difference was, oops, 135 angstrom divided by the 4471. Because essentially what we're calculating now is how far off are we from the known value. So 4471 angstrom. Okay, and unfortunately I didn't give myself enough space for the result. I have to squeeze that down here. So 135, and what we're getting here is a fraction because we're dividing angstroms by angstrom, so the unit totally cancels out, and then in the next step we're going to convert it to a percentage. Okay. And I'm getting something like 0.030. So let me just put the zero, yeah, we're dealing with 3 digits here in terms of the difference. 0.032, and that's just a fraction. Okay. Somebody's putting a little line there. Okay, so now for the last column, E, since we have the fractional, what fraction the difference is of the known value, if we multiply that by 100, we get the percentage. So A, B, C, D, go with E, and I might change the color. Okay, so E, now multiply by 100 to get the percentage. Okay, so then we have 0.0302 times 100. Okay, I can do that in my head because we're just moving the decimal points by 2 to the right, 2 spots to the right. We're making the number larger. So that's just about 3.02%. Okay, let's see, there's a discussion going on in the discussion box. Well, the steps that I just showed you, basically you do that for every single line that you see. And again, since the spectrum comes from a different source than the table, the number of prominent lines, okay, you just don't want to take the prominent lines, so not the really faint ones. But the number of lines that you get from the spectrum, you might be just a little bit different than the number of lines that you get in the table. So you just match the closest ones, and if there's maybe one line in there that doesn't really match very well, then you just drop that line. So you just find the best matches and go through the calculations with through all these steps with those. Okay, I'm going to quickly save. Okay, are there any more questions about how to deal with the unknown spectrum?
Yeah, I think I finally got it. I hope so anyway.
Well, that's a start. Well, you can always send me an email, if you get hung up on something. I mean, I'll be happy if you're starting a calculation and then you get stuck somehow. Just shoot me an email and I'll look over it and I can tell you, okay, this is where you need to be doing this and that, or, you're on the right track, just do this now or something like that. So yeah, I mean, I'll be happy to look over your individual calculations.
I have a question for question one of this. How do you figure out the wavelength?
The wavelength? Yeah, how about if you type your question into the chat box? You said something about the wave. Oh, in number 1? Okay, yeah, let me take a quick look. Okay, hang on. Yeah, I'm just going to take a quick look at the website. Oops. Okay, actually, let's see. Let me see if I can use the sharing of the desktop function. Okay, hang on. I'm going to do share, and if I'm doing this application, then hopefully you'll all see it. Let's see. See what's on my desktop right now. Hang on, I'm still clicking everything. Okay. Are you seeing anything?
Yes.
Okay. So I've gone to item number 9 in the table of contents of the light and spectra, and that's the atomic emission spectra by Joachim Köppen. Happens to be a German, I guess, and he's working in Strasbourg. But if you scroll down, you can see that the topmost continuous spectrum here sort of has a scale that comes with it. So, you see the 4,000 angstrom mark sort of on the left, and then the 7,000 angstrom mark on the right. Then it's sort of subdivided into 500 angstroms, with little tick marks, an angstrom each. So what you could do is you could actually take a piece of paper and, just draw a straight line and then mark the exact same tick marks on the straight line of your piece of paper. See, 4,500, here we have 5,000, 5,500, 6,000, 6,500, and 7,000. Now you can estimate. I'm not going to expect you to, give me the lines of the elements below, down to the single angstrom or something. I mean, I expect a range. I mean, this is how you could do it on your own. Just grab a sheet of paper and trace out at an edge of the sheet of paper, trace out those same tick marks. And then you can move down and, for example, put that sheet of paper at the bottom of the spectrum, and then just quickly guesstimate, okay, this must be, let me just move it up a little bit. Yeah, so if you look at there's a deep purple line. You could draw that too. I mean, it's just a little over 4,100. So you could just say 4,100. This is, 4,300. And then here we have a teal line. So you can just sort of match it up and write. It doesn't have to be more accurate than that. Actually, I'm wondering if you click on it, you might get an actual reading of the line. So if you want to be more exact, see, what did we say? Oh, yeah, 4,100. Okay, so this would be, the blue line would be 4,300 and something. The teal line, 4,400. Sorry, 4,800 and something. So you could do it either way. That's fine, and it doesn't have to be more accurate than that. And then you just pick your 6 favorite elements from that list and write down the most prominent lines and the values for them. I'm just going to go back to our screen here. Are there any other questions about the website? Doesn't look like it.
I'm okay at this point.
Say again?
I said I'm okay right now. I think I've got it on
okay.
that.
Okay. Well, we could quickly talk about the second part of the lab. Let me just turn off the app share again. Okay, and switch it back over to the whiteboard. Okay, let me go ahead and, I think I saved it. Let me just save it again. Can never be sure with technology. Yeah, labeling the most prominent, that's fine. Just so that I get an idea. Okay, you actually looked at that element and you have picked out the most important things. Okay, I'm going to go ahead and clear the slide, and yeah, let's do the Light and Spectra Lab Part 2. That's the Doppler shift. Okay, so basically what happens when we look out into space, every object in space is moving. We're moving around the sun, we're spinning. The sun is moving around the center of the Milky Way galaxy. The stars in the sky, even though, we move as a group, but, things are just shifting ever so slightly. So, some of the stars might move a little bit closer or a little bit further, even though it's just, very small amounts every year. But the further away we look, especially once we get into galaxies, the objects that we're observing might be moving away from us, or they might be moving towards us. So the familiar spectral lines, that we see for each element, like hydrogen or helium. So we know for hydrogen, okay, the first line is at 4,101. The second line was at 4,340, and so on. Well, if we measure the spectrum from the sun, that's the numbers that we get. We see, okay, the 4101 line in the spectrum of the sun, 4,340, those are the hydrogen lines, and we get some other elements in there. But if we measure the spectrum of a different star, then we might get the same configuration. So we might get that the first two lines are just about the same distance in angstrom apart. 100, that would be 239 angstroms apart between those first two hydrogen lines, but the values are not exactly at 4,101 or 4,340. They might be either slightly shorter, towards the 3,000 end, or shifted to slightly longer wavelengths. And we're still looking at hydrogen, but we have this effect in there that if a star is moving, let's say it's moving away from us, then whenever it sends out, let's say, a crest of a light wave, well, by the time it sends out the next crest, it has already moved away from us a little bit. So that stretches out the distance between the two crests that we are receiving. So that actually stretches out that color and shifts it to a slightly longer wavelength. And if a star is moving towards us, then, okay, it sends out the first crest of a particular color. But then when it sends out the following one, in that time it has already moved towards us a little bit, so it has shortened the distance between the two successive crests. And that's why, and of course, if it keeps moving towards us, that's why we see, the whole color then shifted to a little bit shorter wavelength. We experience the same thing with an ambulance. When we stand in the road and we hear an ambulance coming towards us, then the pitch is higher, so it's a higher note. Of course, the volume is going to increase, so it's going to get louder as it approaches, and it's going to get fainter as it recedes. But the Doppler effect is not about the change in volume, it's about the change in pitch, or the change in the note, how high or how low the note sounds. So when the ambulance is approaching us, or the train, or even race cars, we hear a higher pitch from the engine or from the horn, and then when the ambulance whizzes past us, it switches over to a lower pitch. So when it's going away, we hear it at a lower pitch. So this Doppler shift pretty much works for any kind of wave. So it can be a sound wave, it can be a light wave, earthquake waves, what have you. So what we're doing is we're comparing two spectra, and one spectrum, and that's on page 14-7 in the manual. So the first spectrum that we see is our comparison spectrum, and I'm just going to draw a couple of lines here. Just got to switch it over, okay? Okay, and this is going to be our comparison spectrum. So this is what we would measure here on Earth, coming from that element or coming from the sun. Okay, let me just... Yeah, so this is the comparison spectrum, and that is not moving. Okay, I'm going to draw a couple of lines here. We're just going to switch it over to the line again. Okay, so let me also label the lines. Line 1, line 2. Okay, so this is a hypothetical element. This is not any element in particular. Okay, line 3. And let me draw underneath the spectrum of the moving star. Okay. Spectrum of the moving star. Okay. Let me actually use a different color for the line. So that's not the color that the lines would be, but just to show that the lines are shifted. Well, if I'm shifting them to the right, then what would you say? Is that a shift towards longer wavelengths or shorter wavelengths? Well, keep in mind that the left edge starts at 4,000. Yeah, it would be longer. Yeah, because I'm trying to use the same spacing, but I'm just eyeballing here after a couple of glasses of sake, so can't promise accuracy. Okay. Oh, something like that. Okay, and I'm going to label those lines again. 1, 2, and 3. Okay, and the left edge of both of these spectra is at 4,000 angstrom. And just write that down here. And yeah, we're just going to measure all our lengths from the left edge. Okay. Yeah, let me put in that the right edge of the comparison spectrum is at 7,000 angstrom. Let me put that up here in a different color. Because the right edge of the star spectrum since the whole spectrum is a little bit longer, it's at 8,200 angstrom. But we only need the actual length of the comparison spectrum. So now what we're doing, first of all, we need to get a scale factor going. And what we do here, there's not a scale bar, but we know that the length of the box is 3,000, the length of the comparison box is 3,000 angstroms long. So for our scale factor, we have the length of the comparison spectrum. I'm going to abbreviate that a little bit. So that is, actually let me write that out. Because I'll put that down here. So that would be, the right edge minus the left edge. So 7,000 angstrom minus 4,000 angstrom. So that's 3,000 angstroms. So that would be the angstrom value of the length of the top spectrum. Now, we also measure that same length in centimeters. And on my screen, it comes out to be just about 7.3 centimeters. So the length in centimeters would be 7.3. So just as we did before, we're going to form the ratio and get our scale factor. I do want to squeeze it on the same slide, so let me just do that. Let me do that in red. Maybe make a little box to separate it. Okay, so then the scale factor will be 3,000 angstroms divided by 7.3 centimeters. So 3,000 angstroms divided by 7.3 centimeters. And again, you'll have different values because I'm just making these things up and there are specific lengths in the book. So do the calculator really quickly. Yeah, so we're dealing with the length of the comparison spectrum, the bottom of the comparison spectrum. So it's 3,000 angstroms long, and we divide that by the 7.3 centimeters that is long. And we'll get, okay, that's just about 411 angstroms. Hey, let me save before you start doodling. Okay. Thank you. 411 angstroms. All right, did I save this? No. Okay, somebody's deleting my calculation. Okay, just put it back. 4,011 angstrom. Quickly save before anything happens. Okay, so that's going to be our scale factor. So any distance that we measure of any of the lines from the left edge, we're going to multiply by that scale factor. It's actually angstroms per centimeter. Let me squeeze it in here. And then add 4,000 to it for the left edge of the spectrum. So I'm going to do that on the next page. Okay, save it now. Okay, So I'm going to erase this slide. We're going to remember our 411. Oh, that's right. And we need to, before I erase the slide, I need to write down the measurements. Let me just write down the measurement. Okay, it's gone. I didn't do that. Let me see if I can bring it back. I don't know if that's, oh no, it's looking at my computer. I was just clicking at browse. Okay. Let me think real quick. I know it's saved somewhere. Okay, if you bear with me for a couple of minutes, I might be able to save the image and to my computer and then import it back. Okay, hang on just a second.
I pulled it up.
Oh, hang on.
It's under right there under web and content and all that. You go to the snapshots folder and you hit go, and then all of your things are there.
Okay, wait a minute. You said web. I go to.
No, over there to the right under archive where it says content, and then it has a little drop down folder that says default, and then when you pull down the drop down arrow, it says snapshot. You hit that,
Oh, yeah.
and you hit go, and scroll all the way to the bottom, and that's where everything where you hit save goes to.
Oh, good. Okay, that's good to know. Gee, I learned
The
something
one under
today.
that one's blank, but
Oh, cool. Yeah. Very good. Okay. Huh. Yes, I definitely learned something valuable today. There they are. They're not lost. And I mean, I knew they weren't lost, but yeah, it would be kind of awkward to do it a different way. Okay. So, and I got a little bit more space. Cool. Okay, so let's do line one. Quickly measure line one. So in the comparison spectrum, line one is just about at 1 centimeter. And line two is at 1.4 centimeters. I'm measuring all lines from the left edge again. Okay, and the scale factor was 411 angstrom per centimeter. Okay, so let me clear that slide. And so we're going to do the distance of line one from the left edge. Okay, so the first thing is for the comparison spectrum. It was at 1.0 centimeters. And actually we can convert that as to another step, not to crowd things up too much. Okay, and then for the star spectrum, that line had shifted to 1.4 centimeters. Okay, so then we can calculate the actual wavelength. Of the lines. So for the comparison spectrum, that would be 1.0 centimeters times the 411 angstrom per centimeter, and then plus the 4,000. Okay, if we do all that, well, that's actually pretty easy. It's 4,411 angstroms. So that would be the wavelength of our comparison line, and then we get the line from the star. That would be 1.4 centimeters times 411 angstroms per centimeter, and then plus 4,000. I need to put an equal sign up here too. Let's see, for the shift calculated by comparison. In this case, no, you specifically use A minus B, because so the column A would be the comparison line minus the star line, because then the sign can tell you, well, if we get a negative difference, then the star line is larger in wavelength than the comparison line. So, then we have a redshifted situation and the star is moving away from us. But if the star line would be smaller, then we would get a positive difference, and then the star would be blue shifted and moving towards us. Yes, and in that sense, you do want to keep the negative sign because it indicates the direction in which the star is moving, either towards or away from us. Okay, let me calculate this real quick. 1.4 times 411 times, it was 575.4 plus, okay, so 4,575.4. Well, I'm just going to round it to 4,575 angstroms. Okay, yes. So, let me write behind the comparison line wavelength that this is our column A. Okay, and then our star line would go into column B. Okay, and then we have in column C the difference, but this time we specifically go comparison minus the star, and we're not taking the absolute value. So C is the difference, comparison minus star. So that was 4411 angstrom minus 4575. And we'll get, gotta clear my calculator here. Okay, somebody says 164. Yeah, we'll put a negative in front, that's right. So negative 164 angstrom. Okay, well, I'm just noticing something that I've converted. Okay, that's typical. Again, I don't know why we do this differently for both tables. Okay, so you can do it the way I just did it and convert the individual lines right away into angstrom and then take the difference in angstrom, and then continue on to column E, where you write down the original line in angstrom, or the way they actually do it in the table on page 14.8, they don't convert to angstrom until they've calculated the difference. So you can do that too. So alternately, or Um, yeah, let me let's see how can I phrase this. Okay, let me just put a red star there. Red star. Oops, that's not a star. Okay, let me just make a note here for the star. If you convert to angstrom right away. Okay, and then let me put on the next page, because we can keep calculating in centimeters and then just convert the difference to angstrom. So if we were calculating in centimeters, yeah, then we would subtract, I'm going to put that on the next page. Let me just clear this slide. So now we have, let me do that in a different color. So following instructions on page 14-8, so we keep the centimeters. We're going to put down that, so for column A, our line was at 1.0 centimeters, and then it actually doesn't matter if the left edge starts at 4,000 because, you know, we subtract out that difference anyway. And column B, yes, yeah, and we still get a negative shift. Yes, and the shift would be negative 0.4. So B, 1.4 centimeters, and then our difference, C, would be A minus B. So we would have 1.0 centimeters minus 1.4 centimeters, which equals negative 0.4 centimeters. Sorry, I'm old school. I'm putting the 0 in front. But yeah, you can just write point something. That's fine with me. Okay, so now we're ready in column D to convert to angstrom. So it doesn't really matter if you convert right away or if you calculate with the centimeters. Yeah, it goes quicker this way actually, using the centimeters and then just convert the difference to angstrom. So we just multiply our negative 0.4 centimeters by the 411 angstrom per centimeter, and we should wind up with the same negative 164. So I'll just double check that. So 0.4 times 411, yep, 164.4. Yeah, and we had rounded previously, so we'll do so again. And of course, not forget the minus sign. That's so easy to do. Okay, and the unit would be in angstrom. Really hate squeezing things like that. Okay, well, then we note down the original wavelength. And for hydrogen, if I go back to the previous slide, wait a minute. I have an idea because if I save this, And then I'll bring it back. I can bring it back with more space. Okay. Oh, it's still in the snapshot folder. Okay. So our original wavelength was 4,411. Okay. Ooh. Oh no, my letters also decreased. Oh boy, that's gonna look weird. Well, sorry about that, folks. Okay. That's another thing I have to learn how to change the font size. Okay, so then column E. If I right click on it, oh, it doesn't do anything. Okay, so column E is going to be the original of the line that you're working with. Let's just the original wavelength, which was 4,411 angstrom. Okay, everything's going to be teeny tiny now. Okay, and then in column F, we're going to, the same as before, calculate the fractional, what fraction the shift is compared to the original wavelength. So that's the fractional shift. And that is, oh, wait a minute. I think column F is the wrong letter. F. It was D over E, so the result from column D over the result of column E. Negative 164 angstrom divided by 4411. Okay, and again, that's going to give us a unitless fraction. So, dividing that by 4, 1. Okay, so again, we get something really small, 0.0373. 0.0373. Okay, now in G, we have a little bit of a twist. So we're not calculating the percentage, what the percentage of the shift is. But in G, we're actually calculating the speed of the star. And if you look at the Doppler formula, let me just make a, oops, I need to make a line. Because depending on the size of the shift, so by how much the wavelengths shift, that is directly proportional to the speed of the star.
Excuse me, Professor?
Yes. Mm-hmm.
Wouldn't the fractional shift be negative?
Yes, it would be. I just saw that. Yes, it definitely has to be negative. Good catch. Okay. The negative sign there. Okay. Okay, so the speed of the star is proportional to the amount or the fraction of the shift. And if you look at the Doppler formula, so the Doppler shift is basically the shift over original wavelength is equal to the speed of the star speed over the speed of light. So you can solve this just for the speed of the star, so you'd multiply the speed of light to both sides. Let me make a line here. So multiply by speed of light, and then we get for the speed of the star, or the star speed, well, actually, let me keep the sides. So we have speed of light, we just say light speed, times the shift, and then divided by the original wavelength, and that's going to be equal to the speed of the star, or the star speed. So that's the formula that we're going to use up there. So then our star speed is equal to the speed of light. And, well, I mean, you can use the value in meters per second or in kilometers per second. Either way is fine. That just means, you know, if you use the speed of light value in meters per second, then you get your speed of the star in meters per second. Let's see, you say you can't see what I'm writing. Is that too small?
It's cut in half. That second sentence with your calculation, it says multiply by the speed of light in red. It's like someone took a knife and cut a half sentence, and anything down from there you can't see.
Oh, okay. Yeah, let me just rewrite the
No, if
equation.
you actually, if I had my Wimber classroom set on full screen, but when I reduced it to a regular little box, it shows everything. Try that.
Oh.
Well, it got bigger, but mine still won't show it.
Well, I'm just going to type out in words the same thing, you know, since the letters are now really small. Okay, so, yeah, the last line is supposed to be the light speed times the shift divided by the original equals the star speed. So that's basically what I wrote down there, and then, yeah, we can just go ahead and plug in our values. So let's use the speed of light in meters per second. So that's 10 to the 8 meters per second. And then we're multiplying by the shift, which was, we're going to put that in parentheses now, negative, negative 164. Wait a minute. We've already calculated that. That's our fraction, so we don't have to write out the whole thing. So it would just be the speed of light times our fraction, which is negative 0.0373. Okay, and course, the calculator here in my computer is not a scientific one. So we get a minute. Yeah, so it would be like 1.12 or negative 1.12. Let me just write that under here. Okay, negative 1.12 times 10 to the 7 meters per second. Okay, oh yeah, you got negative, 1190. Well, I mean, that's pretty close. You may have multiplied it with the 3 times 10 to the 5 kilometers per second. So you can do that too. So if you multiply your fractional shift with 3 times 10 to the 5 kilometers per second, then you would get, as a result, 11,190 or negative 11,190. So that's actually correct too. Okay, let me go ahead and save this. Well, are there any other questions at this point? The time has gotten away from us a little bit.
I have one really dumb question. When I take my ruler, can't even think of it, I'm so freaking tired, sorry, and I measure this, I don't get 1 centimeter to line A, which I thought is what we were doing in this chart. I don't even get a half of a centimeter. Isn't that what we're measuring?
Oh, no, what the centimeter that I was measuring was referring to, let me pull up that slide again. That was what I constructed, what I made up basically. Let me see if I can go back to that slide. Yeah. So that's basically, I totally made this up out of the hat. It doesn't correspond to anything real. So the centimeter measurement just refers to my sketch on this page on the whiteboard here. But yeah, if you were to measure, yeah, you're right. I mean, in the book, if you measure from the left edge in the comparison spectrum the distance of line 1, you would get something like 0.3 or 0.4 centimeters. Yes.
Okay. Okay, that makes me feel better because we're doing all this and I'm like, I'm still not getting the basics because obviously I don't know how to measure. Okay.
No, you do. Okay, yeah, and then the second line in the comparison spectrum would be at 1.3 centimeters. Yeah, and so on and so forth. Yeah, so you've been measuring the right thing for what it sounds like.
Okay, thank you.
All right. Well, let me jump off and get my kids to bed, and wish you all a good night. Yeah, we can do this again before the next lab. If there are lots of calculations involved or images to look at that, if you're sitting there by yourself, you're thinking, well, what am I looking at here? Okay, so have a good night, everyone, and I'm going to save this and then post the archive and the slides when I get a chance. Yeah, and if you have any questions between now and turning in your lab, you're welcome to take a few extra days. Then you can just send them to me by email. For some reason,